So let's look at a really fascinating reaction called a cyclopropanation reaction. This is an interesting reaction because, as you can see in the product, there's been a 3-carbon ring that has formed. You, of course, will realize that 3-carbon rings are quite strained because of the sp3 hybridized carbons want to form a 109.5 degree angle, and in this product they are 60 degrees. So if you're going to form a pretty unstable product, then you have to generate some kind of a reagent that is unstable. And so that's what's happening with these two compounds, chloroform, CHCl3, and hydroxide. So let's try to figure out what's going to happen here. The carbon, the new carbon in the product, this carbon right here, has to come from this carbon right here, because that's the only carbon that's present in the reagents. So somehow the combination of CHCl3 and KOH has to yield some sort of a carbon bonded to 2 chlorines that is reactive in some way. So if you write out CHCl3 and react this with OH minus, the potassium, of course, is just functioning as a spectator ion. If you look over at the products, you'll notice that there is water has been formed. So that strongly suggests that OH minus is going to function as a base. The proton in CHCl3 is fairly acidic because the minus charge here is stabilized by induction from the chlorines. Once this species is formed, it collapses to form this very interesting species here, which is called a carbene. And you'll notice that in the process, I have formed the water that I need and the Cl minus that I need, remembering, of course, that potassium ion is just spectating throughout all of this. So the key species is this carbene. Okay, so now we have the reactive species, the carbene, and the alkene. When you look at the carbene is an interesting species because it can function as both a nucleophile, so it can be a nucleophile because of the lone pair of electrons, but also this carbon has only 6 electrons around it, so it lacks an octet. Because it lacks an octet, it can also function as an electrophile. We've only seen pi electrons functioning as nucleophiles before, so this is a concerted reaction that is similar to what you saw when you were looking at the hydroboration reaction. So the pi electrons one of the carbons is going to use the pi electrons to form a bond to the electrophilic carbon. At the same time, the nucleophilic carbon, remember it's both a nucleophile and electrophile, is going to use a lone pair of electrons to form a bond to the other carbon. So this is a concerted reaction. All the arrows are moving at the same time. And the product that you would get is a cyclopropane. Now, because all of the arrows are moving at the same time, and because of the fact that you're forming a cyclopropane ring, this is automatically an anti-addition. You can't get the carbon adding to opposite sides of the carbon-carbon double bond because there's only one atom, and that would introduce far too much angle strain. So this is a really interesting reaction. You can do other sorts of alkenes. It doesn't have to be a cycloalkene. So for instance, if I take trans-2-butene and react it with chloroform and base, I'm going to form my cyclopropane ring with 2 chlorines on it. And the methyl groups have to be pointing in the opposite direction because they're pointing in the opposite direction in the starting compound. If I start with cis-2-butene and react it with these reagents, then the methyl groups would be on the same side. This product up here would also have the enantiomer. This product here is not chiral because of the plane of symmetry. You'll notice that I'm not showing any wedges or hashes for the 2 chlorines because one has to be pointing up and one has to be pointing down. They're the same thing, so you tend not to have to show those.